Mrs. Hartman, and I wanted to start demoing some of the old free response questions for the AP exam. So you start getting a feel as we go through the different concepts of types of questions you might be asked. So this question is from 2015. It deals with kinematics and forces, so stuff we've covered so far or are covering, so we can definitely talk about this. So in this problem, you can see that we have a ramp. The block is pushed up the ramp, and it's given an initial velocity of v0, and it's a distance d from the motion sensor. The block's going to travel up the ramp. It's going to stop at some point before the motion sensor, and then it'll slide back down. And it has an angle of theta, and we are told that friction is negligible at this point. So part A says, consider the motion of the block at some times t after it has been projected up the ramp. Express your answers in terms of m, d, v0, t, and theta, and physical constants as appropriate. So physical constants meaning like gravity, g, things like that. And also notice we're not given any numbers in this problem, and that's something that sometimes takes a little practice and adjusting. So this will be good practice. So the first thing we're going to do is determine the acceleration of the block. So that gets right into the heart of what we're doing right now. And so what you can see, I'll move my paper down, is that I started out by just drawing myself a free body diagram of the block. Now, I know that with gravity going straight down and my axis being tipped, that there's a component of gravity in this direction, and there's also a component of gravity that's parallel to the plane of the ramp. And that's the component that's going to be pulling the block down the ramp. And this angle here is also theta. Now, like when I teach my honors physics class, I allow them to go ahead and put these components in their free body diagrams, even though I tell them it's not really correct. But I let them. On the AP exam, if you add these in, you will actually be deducted points. So you need to make sure that if you need to see this diagram, you draw it off to the side in the non-grading area or on scratch paper. So this would be the free body diagram that we need to see to do this problem. And then the bread and butter of all force problems, Newton's second law. Sum of the forces equals mass times acceleration. Some people say force net. Same thing. So my mass times acceleration is going to equal my component of gravity that's parallel to the plane. So this part of gravity is pulling the box down the ramp, and so that's the acceleration. So ultimately the box is going to slow down on the way up because it's going to decelerate the box. And so mass times gravity times the sine of the angle, because the component is opposite that angle, and then I can cancel out my masses, and I have my acceleration due to gravity. Part 2 asks us to determine an expression for the velocity of the block at time t. And so I'm going to start by using this equation from kinematics, and I'm just going to plug in what I know. My initial velocity is up the ramp, and in the problem they told us that down the ramp was positive. So my initial velocity is negative. My acceleration, there's my g sine theta, is in the opposite direction of my velocity, so it's positive, and then there's my t factor. That's all. Then we're asked to find an expression for the position of the block. So I'm going to use this expression to do my position. And my initial position, I'm at d. Again, my initial velocity is up the ramp, so it's negative, so v0 times t. And then my acceleration is g sine theta. There's my t squared and my 1/2. Okay? All right. So now, in part B of the question, we're asked to derive an expression for the position of the minimum x of the block when it is closest to the motion sensor, and we need to still express our answer in terms of the constants that we were given in physical constants. So, for that, I chose to use this equation to get me started. Okay? My final velocity where the block hits its point closest to the motion sensor is going to be 0, because that's the point at which the block is going to turn around. I have my initial velocity. The negative sign dropped out because it's squared. There's my acceleration, and then my change in position. So my final position is x, my initial position is d, and so now I just do some algebra to find x. Okay? Part C of this question, on the axis provided below, sketch graphs of the positions x, velocity v, and a, acceleration, as functions of time for the motion of the block while it goes up and back down the ramp, and explicitly label any intercepts, asymptotes, maxima, or minima with numerical values or algebraic constants as appropriate. So, I actually went this way when I drew my graph. It's not a big deal, but the acceleration one I knew was the easiest because I have constant acceleration. And that's my g sine theta that I found in the in my very first part of the problem. And then for my velocity versus time graph, it's given the initial velocity of negative v naught, and that velocity is going to be changing at a constant rate because I have constant acceleration. It's going to go to 0 at some time t, and then it's going to head back down the ramp where the velocity is positive. But notice that my acceleration value, or the slope of this line, remains the same because my acceleration is constant. For D, or for position versus time, we start at position D, and we are going to have a parabolic shape because the acceleration is constant, but also you've got that t squared factor when you're looking at position. And so it's going to drop down, it's going to come to its minimum, and notice that my time here where it reaches its minimum is consistent with where the velocity becomes 0 over here, and then it's going to head back up and it's going to come back to D. Okay? All right, now let's see what happens when we start adding some friction in. So now the block's going to slide down the ramp, it's going to leave the ramp, it's going to hit a horizontal surface, and now we've got friction. How far does the block go before it slides? And so that is my final part here on this paper. So now notice I drew a new free body diagram because I'm now on a horizontal surface, so I'm no longer on an angle. So that means that my normal force changes, which would change my friction compared to if the ramp had friction. So again, I start with that bread and butter formula. Sum of the forces equals mass times acceleration. Anytime that you're going to use this in the AP Physics exam, I recommend writing this out because oftentimes just stating this is worth a point out of 15. So pick up the easy points. So my mass times acceleration is friction. It's in the negative direction. And now I'm going to substitute in my formula for friction, my coefficient of friction that I was given in the problem, times the normal force. My normal force happens to be the weight because if I were to look at the sum of the forces in the y direction, the vertical direction, they're equal to 0. So 0 is going to be my normal force minus mg. Therefore, mg is equal to my normal force in magnitude. So I can substitute that in. My masses cancel out. And then I have my acceleration, which is a fraction of gravity. So now I'm going to plug into this equation again using my new acceleration, and then I can find the change in x, so how far the block travels after it gets off the ramp. Okay? One last question, or one last part to the question. And this time it says we now have friction on the ramp, okay? And we still have the same initial speed, and we want to draw a velocity versus time graph for this situation, okay? Now, things to notice. You are going to have a constant acceleration on the way up. You're also going to have a constant acceleration on the way down, but they are different. So on the way up the ramp, if you look, if we were to draw a free body diagram, we would have mg straight down. We'd have our normal force perpendicular to the ramp, and friction would be in this direction. So if we were to look at that component of gravity again, and again, never draw these on the free body diagrams on the exam, but it's to help us right now. So some of the forces in the parallel direction for the way up the ramp is MA is going to equal our component of gravity that's parallel to the ramp plus our friction. And we can then substitute in and cancel out our m's. So that means A on the way up the ramp is G sine theta plus mu G cosine theta. Okay, so that's for up the ramp. But on the way back down the ramp, we've got that component of gravity, still the normal force, and this time friction is going to be heading in the opposite direction of the parallel component of gravity. So on the way back down, this would turn to a minus sign. So the acceleration is actually less on the way back down. So that's why you see this slope being steeper than that slope. On top of it, because it takes longer to get back down, that means that if the block lands at the bottom of the ramp at some time t final, then the first part of the trip from the bottom to its maximum point takes less time than coming back down. Therefore, you have to have this intercept prior to t final divided by 2. So, some things to think about, and tips with forces in terms of your free body diagrams. Don't draw the components in, just draw the forces, do the components off to the side, and you should be all set. Let me know if you have any questions. You can find other practice problems like this at the AP Central website, and good luck with forces.